Okay, so in this video, I just want to show you how we solve example problems with accelerated motion. We have a car that accelerates from rest to 60 miles an hour, which is about 26 meters per second. So a simple diagram just includes a number line, which represents our road. We've got a car which accelerates to the right. Our variable list, we have the distance the car goes, we have the velocity of the car at the beginning, we have the velocity of the car at the end, we have the acceleration, and we have the time. And for those, we want to read the problem and see if we can figure out any of them. So this 26 is the speed of the car after it is accelerated. So it is the final velocity. This is 26 meters per second. 8.0 seconds is the time. It's the time over which it accelerates. 8.0 seconds. It says it accelerates from rest. So that's a key word that tells us that the initial velocity is actually 0 meters per second. And we are asked to find the acceleration. So we're going to make a plan here. We always start with this. We're going to solve. We've got to look at our toolbox and see which equation we're going to use. And it's going to be that the final velocity equals the initial velocity plus a times t. And we're going to solve this for the acceleration. That's our plan. Now I want you to solve it algebraically. That means that you get a by itself. So that's going to be v final minus v initial. Divide both sides by time. And since the initial velocity is 0, it drops out. So the acceleration is going to be the final velocity divided by the time. We can now evaluate that numerically. That's going to be 26 meters per second divided by a time of 8 seconds, and 26 divided by 8 is 3.25, and that's going to be meters per second or meters per second squared. So that is the acceleration of the car. The second question asks us how far does it go while it is accelerating? So now we're trying to find delta x, how far it goes. And so we need to use one of our different equations. We don't need a new diagram. We don't need a new variable list. We know the acceleration now is 3.25 meters per second squared. We've got to use an equation that's going to help us find delta x. So probably the easiest thing to do here for part B is to say we are going to solve delta x equals v0t plus 1/2 of a t squared, and we're going to try to find delta x. Now we don't need to make an algebraic solution because it's already there. Move this up a little bit. So we just need to say delta x equals, since the initial velocity is 0 from our variable list, anything that it's multiplied by will also be 0, so that just goes out of our equation, and we get 1/2 a t squared. That's a solution for an algebraic solution. We can now plug that in. That's 1/2 of 3.25, and that's meters per second squared, times the time, which is 8.0 seconds squared. So it's 1/2 at squared. We can plug in our numbers, and we get a distance of 104 meters. We have meters per second squared times second squared. The second squared cancel, and we're left with meters. And that is the distance it goes, delta x. So now we got to think about three things. Does it have the right units? Meters? Yep, that's right. Does it make sense? Is it reasonable? Does a car go 100 meters, like down the length of one side of a track while it's speeding up? That seems to be reasonable. And what about significant figures? Well, we can really only have two significant figures, because we had two significant figures here in the final velocity. So really we should write this as 1.0 times 10 to the second meters. And so that's the solution with the correct amount of precision reflected in the answer. Okay, so when we're solving problems, that's how we do it. For each problem, I need to see a diagram of some sort, a list of your variables, and I especially care about the plan. Tell me what you're going to do. If there's more than one step, enumerate it. Call this step 1, step 2. An algebraic solution, and then a numerical solution, and then check if it's reasonable. We were asked for the acceleration, so I'm going to put a box around this since it's the result that I was looking for. And that's how we solve the problem.